Hello everyone. This presentation will be documenting the designing, prototyping, and overall process of developing the revolving door sensor for the main entrance of the Bunker Hill Community College B building. The design team. The design team behind the project consists of four engineering students: Trevor Smith, Alexander Aguilar, um, Abdullah Ben Mohammed, who was the civil engineer, and myself, who was a mechanical engineer. The goal of our project was to create a sensor device that will monitor foot traffic on the school's campus, providing a way to accurately estimate the amount of students and faculty on the campus at any given time. In an emergency, a major concern for administration, faculty, and response teams alike is the ability to account for all personnel in the building. Response teams need to be able to account for everyone during and after an emergency, just to make sure that they can provide better communication to emergency teams, students, their families. Just in general, enhanced communication provides opportunities for better coordinated evacuations and direction of faculty and students in highly populated areas. The method we chose to achieve that goal is tracking the ingress and egress of the pair of revolving doors that are in the B lobby of the college. The ideal design team is essentially consisting of the team we actually already have in place. There are four main pillars of this project. The bio or life component. The final product should in no way be detrimental to human life or well-being. Biomedical engineers are proficient in applying engineering principles to medicine and healthcare. There's also how the end product will integrate into the building's existing structure. This is the civil engineer's main concern. They work with environments to ensure the design of the product is harmonious with the building and its design. Mechanical engineers are focused on the actual product itself, focusing on optimal design in terms of size, material, aesthetics, etc. Electrical engineers aid in designing the wiring which will use to provide power to the system and transfer data to the BHCC network. Our criteria for success. The goal of this is to provide a proof of concept that are and provide a potential people counting system for the school. One that's affordable, effective, and would work in an emergency. That will require no modifying of the building entrance, wouldn't get in the way of the flow of traffic, would be low profile, and a high efficiency design that requires little to no maintenance. Lastly, it would adequately account for the ingress and ingress within the egress of the college. Of course, with any project, there are constraints. There are limited means to accomplish the previously mentioned criteria and develop a successful proof of concept. For starters, there's time. Time is limited. There's a defined due date in which the product must be finished and unveiled. There is a budget which must be adhered to. There aren't unlimited funds in which to make costly mistakes or purchase extravagant materials. The personnel involved is restricted to the design group previously mentioned, and the finished product must be hazard-free. There's no room for a product that is even remotely dangerous. It has to be completely safe and not a danger to those who pass through it. The materials are restricted to what's available over the counter. They have to be inexpensive, sort of generic. And the project team must be self-motivated and self-managed. We don't have someone who can look over us and make sure we're on track. So before beginning the design, we had to evaluate, theorize, and compare existing solutions to for existing solutions, we had to compare and evaluate different existing solutions that we thought up. One of the first was placing two pressurized sensors on the floor and the revolving doors, one on each side of the exits. So whenever one is stepped on, it adds or subtracts from the total occupancy count. Another solution was an infrared sensor attached to door handles or on top of each door. So whenever someone enters the revolving door, either um, through exiting or entering, the sensor would pick up whenever the glass or handles are touched, either adding or removing from the occupancy count. An ID sensor was another solution placed at the entrance and exit of the revolving door. Um, ID sensors were placed there to scan, notifying security when someone enters or exits. It specifies who enters and adds them or subtracts them from the total count. Another solution was a motion sensor. It would be placed on top of the revolving door, and whenever someone enters or exits the building, the sensor will pick up the motion and relay it, distinguishing between if they were entering or exiting. Another one would be a kinetic sensor, which we placed on the revolving door itself. So whenever the sensor exceeds a certain set bar of motion, when the door is moved, it would add to the total occupancy count. Another solution was a camera. This would be placed in the main lobby, and someone would be watching it. It would recognize this camera would have facial recognition software and would count the faces as they come and as they go. So what we used to sort of evaluate and compare all these existing solutions was a pug chart, which is basically a decision matrix. Each potential solution was evaluated on 9 different criteria, and each area of critique was given a weight. So some criteria held more value and its importance to the finished product, and to the accuracy of the areas of critique were accuracy, effects on traffic flow, maintainability, reliability, cost, safety, data usefulness, manufacturability, and operating environment. After going through those and sort of evaluating them, we came up with preliminary recommended solution. So ultimately, we decided to go with the pressure sensor design. It consists of a rubber slip-resistant platform, which houses a simple circuit, and the platform acts as a mechanism which, when stepped on, depresses and completes the circuit. And that each completed circuit is registered as a count. It also houses a pressure sensor, so when the pressure sensor detects a force greater than its standard, it will be reported back to the main system. This will account for one person entering or exiting and add one ingress or egress to the total. 2 sensors will be installed on either side of the revolving door, one on the ingress side and one on the egress side. We decided that the shape of the pad should be triangular. It would fit the space of the revolving door the best and reduce the risk of people stepping on the plate at the same time, because you don't want 2 different people stepping on the same plate and messing up the count. So the pressure plate was a fairly straightforward decision to make. It was a solution that kind of stood above the rest. It did, however, come with some drawbacks, some concerns, and potential risks, as any project comes with. But it was imperative to evaluate those risks on their likelihood as well as the severity of the consequences should any risks come to fruition. So, we took a look at the different ones, and we just wanted to make sure that we evaluated them thoroughly. Such as one of the first ones we looked at was rainwater potentially leaking into the revolving door. This was moderate likelihood, but would be very high consequence. There might be a person who is too heavy or who jumps on the sensor and breaks it. Low likelihood, moderate consequence. During an emergency, if the volume and the velocity of egress causes the system to fail, That would be a problem that was low likelihood but high consequences. On the accuracy thrown off by environmental factors such as an earthquake or something like that, that would be low risk but very high consequence. There were some other ones that we went over, such as the door clearance, not allowing the sensor to have enough space to fit underneath. Very low likelihood, but high consequence. We wouldn't even be able to use this method of counting. And those were pretty much it. Oh, the last being if someone dropped something in front of the door and it got caught. Um, it's difficult to imagine that something as inconsequential as a floor pressure pad would have any sort of social or ethical dilemma. But every new invention or redesign presents some sort of issue that needs to be resolved or confronted. Keeping diligent track of how many people enter and leave the building at all times can be considered an invasion of privacy. It's also entirely possible that this knowledge, if fallen into the wrong hands, could be used for malicious purposes. These factors just must be taken into account and acknowledged. Furthermore, the designing and implementation of the pressure pad, we considered it a utilitarian in nature and deemed that the overall intentional benefits outweigh any tangible or potential drawbacks. Next, we have the economic analysis. The floor pressure has a relatively low overall cost in comparison to the alternative potential solutions. The materials needed were both few in number and fairly inexpensive. There was a $60 Arduino board, two pressure sensors, a flex sensor, altogether coming to a whopping $220. Next, we had the technical analysis. The floor pressure sensor uses a gravity-dependent concept. The mass and weight of coming and going students and faculty applies a downward force to the pressure pad. This force completes the simple circuit within the encasement and initiates a single count. The design also makes use of the principle of elastic deformation. It's important that when the weight is applied to the floor pad, the ensuing depression, the one which initiates the count, is both temporary and self-reversing, meaning it goes back to its original state. These two concepts come together and complete the floor sensor design and account for an accurate representation of the individual students and faculty who come in and out of the building. And that is how we came up with our concept. That is how we provided a proof of it. And that was our conclusion. Thank you.